for other objects, other shapes, like there are some common shapes. I'll give you the formula first, and I'll try to justify one or two of them. Okay, so if you have a ring like this, okay, so this is the first one, a thin ring. The moment of inertia, if this is r like this, the radius is r. The moment of inertia of a ring is does it have a half? Sometimes I always forget that. No, it's just mr squared. And understand what each variable means. This is the radius of the ring, which is different from the previous r. That was the r before, even though we use the same r, that r is the distance. So it's very important when we write down these couple of formulas, you need to understand what does the r stand for, or for that matter, what does every variable stand for, okay? So that's the radius of the ring. Before that was the distance from the axis to the mass. And here we're trying to rotate a ring around the center like this. Okay, so if you want to rotate this, that's the radius of the ring, and this is the total mass of the ring. Okay, so it looks like a point mass formula, but the variables mean something different. Okay, and if you fill in the ring, so this is a thin ring, so all the mass is sort of distributed over here. Okay, so I'm not justifying just yet, I'm just giving you the formula over here. And for a disk, okay, when we say disk, usually solid disk, so like this, right? So it's the mass is filled in. So with a disk of, so this is a ring of mass m, this is a disk of mass m, rotate around here, and with radius r, the moment of inertia for that is actually half mr squared. Okay, so which one's easier to rotate? This is 1/2 mr squared, this is mr squared, right? So it's actually half as easy to rotate it around the disk. Why is that, right? You might think that this is harder, but now this is the same mass. I'm talking about if you have the same mass, then this guy, right? All the same mass, let's say both of them is 10 kilograms. All the 10 kilograms is concentrated at the outer rim, whereas here the 10 kilograms distributed around the disk, right? So as you know, every point mass, if I have a point mass, if I try to rotate a point mass, the closer to the axis of rotation, since I'm so notice when I give you the formula, it depends on the mass, the shape, and also, so it depends on three things, right? It depends on the mass, the shape, and the axis of rotation. Is that just below the glare? Yeah. All of them, I need to tell you where I'm rotating about as well. So a lot more points are closer to the center of the axis of rotation. So this will actually be easier, even though both of them is 10 kilograms. Okay, I'll give another one that is common that you'll probably use is for a sphere. So if you have a sphere and you want to rotate above the center like that, then I sphere, the moment of inertia, is 2/5 of mr squared, and m is the mass of the sphere, solid sphere, and r is the radius of the sphere, and the axis of rotation is from the center. Okay, and I'll also give you three more. These are all in the book, and this is one of the very few cases where I'll point out maybe one of them where it comes from, one or two, depending if I have time. But in the exam, you will not be asked. To reproduce this when you need to use this. So you'll be given these formulas, and it's in your textbook, page 260. Okay, and you can find a lot of the common formulas. I think they have 8 of them, but yeah, I think they have 8 of them, but I'll tell you the 6 most common ones that we'll use. But if you ever need the moment of inertia of a given shape, mass, and axis of rotation object, you usually be given the I. But for point mass, you need to know how to figure out if you're given couple of point mass, just like the previous example, you need to know how to get that. But anything more complicated than couple of point mass, like a continuous object like this, you'll be given these formulas. Okay, so for a rod, The next one is for a rod where you rotate about the center. So a rod of mass M and, sorry, 4, 5. And same thing, a rod of mass M, but you rotate it from the edge. Rod of mass M. Okay, so this one is rod, center. So rotate from the center is 112 ml squared. And L is the length of the rod. Notice some books use R as well. Our textbook use L, but some books use R. But this time the R is not from here, right? It's the whole thing from here, okay? So be careful for that. And I for the rod, but this time rotating from the edge is 1/3 ml squared. And L again being the whole length. Okay, so most of us don't have these things memorized, and it's a table you look up. So that's the same thing you're gonna do. You don't need to memorize. This is one of the few cases, right? It's an important formula, but you don't have to memorize this unless you're an engineer. Maybe you need to use these on daily basis, and you want to reckon. After you use it a couple of times, I recognize some of them, but no, I don't waste my memory to commit them to memory. But yeah, you'll need to know how to use them later on in some of the next equations, and also get an intuition of them. But both point mass, you need to figure out how to do point masses. Also get an intuition, right? So this is the same mass, same length. Which one's easier to rotate? Okay, 12 is a larger number, so it's this one, right? No. 112, 12 is a larger number than 3, but 112 is smaller than 3. So this has a smaller moment of inertia, which is a smaller rotational inertia, right? That means it's easier to rotate than this, okay? How much easier? Well, you can do a quick ratio, right? The rod from the center divide by I of the rod from the edge, okay? So that's 112 ml squared, 1/3 ml squared, same mass, same length, so ml squared cancels out. So you have 3/12, 1/4. So it's a 1/4. So the moment of inertia of this over this is 1/4. Okay, so you can also put that to the other side. So I from the center is 1/4 of I rotating the rod from the edge. So you see that it's 4 times easier, right? This number is 1/4 of this number. Okay, so this must be a larger number, 4 times larger than this. Okay? Or you can put the 4 over here, depending on how you like to look at your equations. Okay, so the last one is a rectangle, rectangle disk. I guess it's not a disk, it's a plate. So if it's a rectangle like this with certain length and certain width, and you rotate it about the center, it is 1/12 of m and then length square plus width square. Okay, so does this make sense? Yeah, if you think about it, it's really the same as rotating. What if the width is 0? If the width is 0, you just have a rod rotating it at the center. So it's exactly this one. If you have the length is 0, you just have a rod with the width. If the length is 0, right, you just have a rod with the width being the length, right? So it's again 1/12 mw squared. Okay, so it kind of makes sense. All right, so good. So these are, like I said, you don't have to memorize them. You need to know how to use them. All right, so just to give you a feel of this, maybe I'll explain one where it comes from. The ring is sort of the easiest to see why that is true. Okay, so remember we have calculated the moment of inertia with 2 masses, radius r apart. Okay, so let me call this capital M. Yeah, instead of capital M, I'll call this m/2. All right, so this guy has mass capital M/2 because I want the total mass, right, to be m. Okay, so it will be m/2 plus m/2 like this. Okay, what's the moment of inertia for this guy? Well, all right, so rotating about the center, right? Two masses here of each with mass, total mass, half of the total mass. Okay, so the moment of inertia for these two guys, right, is, well, it's just this, the moment of inertia, this plus this. So one of them is m/2 and r squared, right? Plus another one. So I just need to multiply by 2. What's the answer? It's the 2 cancels, right? So yeah, I'll keep that so you can see the pattern over here is mr squared. Now, what if I take a knife and chop this in half? So now I have m/4 and m/4, right? And so basically originally here, I'm taking mass m and chopping it into 2 and putting it on both sides. And I realized this is the moment of inertia, okay? So of the total mass r squared. Now, if I take it and chop it in half again and put it in 4 corners, so each of them is 1/4 of the total mass. What's I, right? In this configuration with chopping it into 4. Well, it's 4 times. They're all sort of equal distance from the center. So 4 times of mass over 4 r squared. So it's again mr squared. Can you see where I'm going with this? Now let me chop this in 8ths, right? So I'll put 8th, 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 8th over here and put another 8th over here, radius r away, radius r away, radius r away, and 8, radius r away. So distance r away from the center. 1, 2, 3, 4, 5, 6, 7, 8. Yep. All right. So what is my moment of inertia? I have 8 of these, but each one is m/8 times r squared. So mr squared. You see where this is going, right? So now what I could do is I can chop it into n times and multiply by n of those. So that will give me a ring if they are all distance r apart. All right. So the answer is just mr squared. So technically, a ring is when I take the limit. So here I should insert the limit of capital N goes to infinity. So I take the mass m, right? The total capital mass m, and just assume it's little pieces of mass, right? The little pieces of mass, and I have infinite ones of them, and just add them up. And it will be this formula, but you see n and n cancel. So technically I have infinity divided by infinity, but don't take the limit just yet, right? So simplify your equation first. So you have mr squared. Now you take n to the going to infinity, but here there's no more n. So it's just mr squared, right? So you see where you can figure that out from. And once you take anything with limits to infinity, that's where calculus and integration and differentiation sort of come in. And some of these numbers with 112, actually they all sort of follow that rule of, follow the idea of, let me chop this into little pieces. And instead of calling it, so each piece m/n, we can call that delta m, right? It's a small change in n. And if I take the conceptual limit of n goes to infinity, we say, we write this instead of delta m, we write dm. So whenever you see something like dm, it's just a small piece of mass. And if you ask how small, it's infinitesimally small. Infinitesimally just means you're chopping this. It's taking m dividing almost by infinity. Okay. So you can't, if you divide by it, your calculator will blow up. So you can't really do that on the calculator, but you sort of have the concept of it, and the strategy of dealing with calculus is basically try to get rid of any n's before you actually take the limits. So it's something like that. Right. Anyway, so the conceptual idea is you just take each little ones as a little piece of mass and calculate that they have all different distances and do the correct limits, do the correct integration, and you'll get the correct factors out of this, which is sort of beyond the scope of this course, but that one's easy enough to explain, and you can see where these come from. Okay.